Okay, so let's look at a titration curve of adding the sodium hydroxide to the formic acid. So this is the same curve that we were looking at where we were calculating the pH values. So we calculated the pH as 2.37. Remember, this is when no sodium hydroxide has been added. We only have the weak acid. Then we start adding the sodium hydroxide. It neutralizes the weak acid. We start creating some of that conjugate base. So we have a buffer system. And remember, at the midpoint here, this is our half equivalence point where the pH equals the pKa. And notice that as we get closer and closer to the equivalence point, we have this rapid jump in the pH. So we have a rapid increase in the pH. And then at the equivalence point, the pH is 8.23. And this is because you have the formate ion in there, and that's determining the pH because all of the sodium hydroxide has been consumed and all the formic acid has been consumed. And then after the equivalence point, we still get a large increase in the pH as we start adding the sodium hydroxide, but with each addition of the sodium hydroxide, the change in pH becomes less and less. So a couple of things that we discussed when we were looking at the titration curve of a weak acid with a strong base. The initial pH is that of the weak acid solution, and we calculate it like a weak acid equilibrium problem. And before the equivalence point, the solution becomes a buffer. So we calculate the moles of the protonated acid and the moles of the conjugate base using reaction stoichiometry. And then we can calculate the pH with the Henderson-Hasselbalch equation using the moles of the protonated acid and the deprotonated acid. And we also said that at the half neutralization point, the pH equals the pKa because the amount of HA and A minus are the same. And when they have the same ratio, that fraction becomes 1 and the log of 1 is 0. And this is why the pH equals the pKa at the half neutralization point. Here's some other things that we learned by looking at the titration of a weak acid with a strong base. At the equivalence point, the moles of the weak acid equal the moles of the base, so the resulting solution only has the conjugate base anion in it before the equilibrium is established. So we calculate that pH like a weak base equilibrium problem. So the solution is basic due to the formation of the conjugate base because all of the weak acid has been consumed and all of the strong base has been consumed. And then beyond the equivalence point, the hydroxide ion is in excess, and so we can use the excess hydroxide concentration to determine our pH. Now we can also titrate a weak base with a strong acid, and the titration curves look very similar to the weak acid and weak base, except this time the pH is decreasing. So in this titration curve, we've got a volume of HCl being added on the axis, and on the y-axis we have pH. So again, remember when no HCl is added, this is type 1 calculation. This type 1 calculation is only done once because remember this is a weak base. So you have the NH3 plus the water, and it establishes an equilibrium to make the protonated NH3, so that's the hydronium ion and the hydroxide. So at this initial value where you don't have any HCl added, if you know the 0.1 molar, so 0.1 molar and nothing else has been added, minus x plus x plus x, so the Kb equals x squared over the 0.1 minus x. And the x value is x is the hydroxide ion concentration. If I take the negative log of that, I get my POH, and 14 minus the POH gives me my pH. But once we get in the buffer region. So remember, the buffer region is anywhere in between that initial value when no acid has been added and at the equivalence point. Anywhere along there is the buffer region. But the effective buffer region is going to be where you have that tangent line where it overlaps with the half neutralization point, where the tangent line overlaps with your titration curve. So remember, at the half equivalence point, the pH will equal the pKb. And this area in between here, this plus or minus 1 unit of the pKb, is the effective buffer region. And in the buffer region, we can use the Henderson-Hasselbalch equation. And then at the equivalence point, remember, this is our type 3 calculation, and all of the weak base has been consumed by the strong acid, and there's no more strong acid left. So that weak base, so if we're looking at NH3 plus HCl, and that's a one-way reaction, all of your ammonia is converted to, all of your ammonia becomes ammonium, and you've got the chloride anion. So at the equivalence point, you have the ammonium, no more ammonia and no more HCl. So if this is acidic, then the pH should be acidic at the equivalence point. So this is why at the equivalence point the pH is acidic, because all of the weak base has been converted to the weak acid. And then after the equivalence point, the rest of the curve can be calculated using our type 4 calculation. And remember, type 4, we're just looking at the excess. So we have an excess strong acid. Once we know the amount of excess strong acid, the amount of excess HCl, we can take the negative log of the H plus concentration, which is in excess, to get our pH. So notice that the titration curve calculations for the weak base strong acid are very similar to the weak acid strong base. Now, you won't do a titration of a polyprotic acid in lab, but we're going to discuss it some here. If the first Ka, so the dissociation constant for the first acid, is much larger than the acid dissociation constant for the second proton, there will be two equivalence points in the titration. And the closer those Ka values are to each other, the less distinguishable the equivalence points are. So in this graph, we're looking at the titration of 25 mils of 0.1 molar sulfurous. So we're looking at the titration curve of 25 mils of 0.1 molar sulfurous acid with 1 molar sodium hydroxide. So again, pH is on the y-axis, volume of sodium hydroxide is added on the x-axis, and we have an inflection point here. This is the first equivalence point. So this is the removal of that first proton. So remember that sulfuric acid, the sulfurous acid. So we remove that first proton. So if we're neutralizing the sulfurous acid, if we had one equivalent of sodium hydroxide, we've removed the first proton from the sulfurous acid. So that first proton combines with the hydroxide to form water. You still have the sodium ion, that's a spectator ion, and that creates the HSO3 minus. And if you continue to add another equivalent of sodium hydroxide, the HSO3 minus plus another sodium hydroxide equivalent will give you another water molecule, another sodium ion, that's a spectator ion, and the SO3 2 minus ion. So when we do these titration curves, we need to be able to monitor the pH. And the general method for monitoring the pH during the course of a titration is to measure the conductivity of the solution due to the hydronium ions. And this is done using a probe that specifically measures just hydronium ions. So this is what the pH meter actually does, and this is why that pH probe has that permeable glass membrane, and it has to be you have to be very careful not to let it dry out so that you don't destroy it, because the hydronium ions actually have to pass through there, and the pH meter is converting the conductivity that it measures into a concentration of the hydronium ions. Now during the titration, the end point of the titration is reached at the equivalence point in the titration. And remember that equivalence point is that inflection point of the titration curve. If you just need to know the amount of titrant added to reach the end point, we often monitor the titration with an indicator. So this is just showing you a setup where we have a solution that we're titrating with sodium hydroxide, and there's a pH probe in the solution, and it's connected to a computer that plots the volume with the pH. You will be creating your graphs in the lab by hand, and you will add volumes of your known concentration from your burette to your titrant. So you'll be measuring your volumes and measuring the pH, and you'll plot the volume versus the pH. So we're going to take a little bit of time to focus on indicators, and many dyes change color depending on the pH of the solution. And you should have seen this already in your lab when you were determining the equilibrium constant for bromothiol blue. And these dyes are weak acids, and they establish an equilibrium with water and the hydronium ions in solution. So here we're representing the indicator as a weak acid, and the weak acid, when dissolved in water, will deprotonate to form the conjugate base. So this is what I'm representing with the IND minus plus the hydronium ion. And the color of the solution depends on the relative concentration of the deprotonated and protonated form of the indicator. When you have equal amounts of the protonated and non-protonated form of the indicator, so equal amounts of the acid and the conjugate base, the color will be a mixture of the colors of the protonated form and the deprotonated form. When the deprotonated form of the indicator is much larger than the protonated form by more than a factor of 10, the color of the solution will be the color of the deprotonated form of the indicator. And when the deprotonated form of the indicator is much less than the protonated form of the indicator, so a ratio of 0.1, the color of the solution will be the color of the protonated form of the indicator. So here is a common indicator, phenolphthalein, and this is the form of the phenolphthalein in acid solution. When you add a base, so when you add sodium hydroxide, the phenolphthalein undergoes a chemical change. And when it undergoes a chemical change, it produces this new compound here, and this compound has the dark pink color, the hot pink color. So notice that the carbon-oxygen bond is broken here, and those electrons get moved onto the oxygen, and so this is why this oxygen has a negative charge. But then you have some other changes in the reaction too. So this hydrogen has been removed, so this OH group has been deprotonated. So you have an O minus here, and this hydrogen too has been removed, so it's been deprotonated here. And when the hydrogen is removed as a proton, it leaves those electrons behind, so those electrons then go to form a double bond here. Well, these electrons in this double bond get moved to this position. Well, then the electrons in this double bond get moved to this here. So this is why we have this rearrangement of electrons in the double bonds in the carbon system. And it's these changes in the compound that cause the new compound to be colored. So looking at this titration curve of the indicator, notice here at the equivalence point. So at the equivalence point, remember you have equal amounts of the conjugate acid and the conjugate base. So this is where you have that slight pink color. So you have half of the colorless form the phenolphthalein, you have half of the dark pink. So remember, this compound is colorless in the acid solution, and this form is hot pink. So once you start putting the phenolphthalein in a basic solution, when you have some excess hydroxide ions, those hydroxide ions will react with your indicator, so it will react with the phenolphthalein, and those hydroxides then go to deprotonate the phenolphthalein to form this hot pink colored complex. And of course, this reaction is reversible. If you add an acid, you can then protonate that O- there, and you can protonate again that oxygen and have that rearrangement happen to reform the colorless form of the phenolphthalein. Methyl red is another common indicator, and it goes from this reddish color to a yellow. So in the acid solution, so here we have a picture of the methyl red in a pH of 2. This is the form of the methyl red. So notice this nitrogen here. This nitrogen has a hydrogen attached to it. And remember, this compound is this pink or red color. If I add a hydroxide to this compound, the hydroxide will remove that hydrogen, and you have an N- here. And when you have this chemical change, this is where you get the change in color with the hydroxide added, so in a basic system. So this compound is yellow. So when you add the hydroxide, you remove that proton, and this becomes yellow. But if you want to reverse the reaction, you can add an acid, and the acid will protonate the nitrogen, and then it will return to its red-pink color. So there are many different types of acid-base indicators, and this is just a list to show you that not only the colors that they change, so like bromophenol blue goes from yellow to blue, it also tells you at which pH the indicator undergoes this color change. So you have to choose your indicator based on your system. Now I want to draw your attention to phenolphthalein. Phenolphthalein changes color in this range between 9 and 10, and you go from colorless to pink. So if the color change doesn't happen until the pH gets to around 8 or 9, why in the world do we use phenolphthalein when we look to titrate like a strong acid and strong base? Because the equivalence point is at 7. This doesn't change color until the pH is 8 or 9. Wouldn't we have missed the equivalence point if we're trying to stop the titration when we have exactly the same amount of strong acid and strong base? Well, the answer lies in the titration curve. So here we have that titration curve of a strong acid with a strong base. And remember, we said at the equivalence point the pH is 7 for a strong acid, strong base system. And if we're using phenolphthalein to determine this endpoint, it changes at a pH between 9 and 10. Well, the 9 and 10 region, this is still the very sharp increase of the pH compared to the volume added. So you have a very small change in volume for a large increase in pH. So if we miss it by just a little bit by the color change, it's not by very much. So this is why it's okay to use phenolphthalein as an indicator to determine the endpoint of the reaction. And remember, this is where we talked about earlier where the endpoint doesn't necessarily give you the equivalence point. They should be as close to each other as possible, but they are slightly different. So we will stop the reaction. We start seeing the pink being formed. So this is the end of our discussion for acid and bases and indicators. The next set of video slides will begin discussing solubility constants as part of the end of our chapter 16.